All right, the next section we have is 13.4, which is curvature. So if curvature is on the exam, it's one of those topics that sometimes is, sometimes isn't. Um, Literally being asked to calculate curvature. So this section is called, just so, let me clarify here. This section is called curvature, but there are other very important topics that are commonly on the final exam, such as given some parameterization, finding what the unit, normal, and tangent vectors are. But they may not ask you to actually calculate curvature, kappa of t. If you are actually asked to calculate the curvature, there's four formulas for this, and some of those formulas apply in certain circumstances, and others are generally applicable. If this is a normal semester, I'm making these videos right now during the spring of 2020. So right now, it's a Gradescope exam, so you won't have the formulas on Gradescope, but you're at home, so you can look up the formula. If you're watching this video at a later date, then if it's on the exam, you'll be given the formulas. So either way, don't worry about it, is my point. So, and that's kind of what this says. For these two things right here, essentially we have the following picture. So R of t, let's say, traces some path. So let's say this is the path traced by some parameterization r. Then at some point, let's say right here, there are two special vectors. There's this vector, which is the unit tangent vector. And remember that your r prime of t, r prime of, I'll just forget the variable, r prime, that's your velocity vector. That could be really long, right? If you're going really fast at this moment in time, then the vector would, r prime would be very long. If you're going very slow, maybe the vector is very small. So regardless of the length of the vector, they're all pointing in this direction, but the length has to do with what your actual speed is. If we take r prime and we make it into a unit vector by dividing by its length, that's going to scale this vector either up or down so that it has length 1. And that's exactly what the unit tangent vector is. The unit tangent vector right here is just your velocity vector made into a unit vector by dividing by its own length, or velocity divided by speed. This is a unit vector. Hence the name unit tangent vector. The other special vector we have is the unit normal vector, which in this case is right here. This unit normal vector always points in the direction of bending. So t is in direction of motion. The unit normal is in the direction of bending. Or cupping. Sometimes in 2 dimensions it's easier to think of this as like cupping inward this way. Like you're taking your hands and you're bending it inward. If it's like a rod, you'd have to bend it this way inward. So that's your unit normal right there. These two will always be at a right angle. So this will always be at a right angle. And the way you find the unit normal vector, this is the derivative of the unit tangent divided by its own length. There is another vector that is sometimes mentioned, but it rarely, if ever, shows up. It is the binormal unit vector. Which is b. This is the unit tangent crossed with the unit normal. And if you take the cross product here, that produces a third vector. I'm trying to draw this in perspective here. So this is supposed to be like pointing up, like up, out, off the screen, kind of. I'm not sure how well that is captured here, but that's sort of what's going on here. We have a right angle from here to here, we have a right angle from here to here, and we have a right angle from here to here. So this is pointing like off the screen, or out of the screen. This would be B. So together, these three vectors, T, N, and B, they make this moving coordinate system that travels with you. Because at this point, there's its own T, N, and then there's a B coming out of the screen as well. Sometimes you're asked to just calculate this. You don't have to do anything with it. So it's essentially just taking a cross product.